All right, so let's finish up this proof, right? So I mentioned in the last video we need the Jacobian of the transformation. Again, we have two different variables here, and it's not the same as just, take as we did when we were working with one variable and we were converting from x to z. So this Jacobian is a matrix, and what we need is the determinant of this matrix, right? And I said also we're going to take the absolute value of the Jacobian. To calculate the Jacobian, you calculate the determinant here. And the determinant, let's set this up. So we need the derivative of z with respect to r. If you recall, let me go back for a second here. And the first one, so we had z is equal to r cosine theta, and y was equal to r sine theta. And as you recall before, we substituted these into the equations. We get the hypotenuse in this case, which is r squared. We could just substitute that, right? R squared for z squared and y squared. So that's what we're doing here. But it's important to know what z is and what r is here. And we need to take the derivative with respect to, for z with respect to r and with respect to theta, and then for y with respect to r and with respect to theta. So that's what we're doing with the Jacobian here. So we're taking the derivative with respect to r, of z with respect to r and z with respect to theta, and y with respect to r and y with respect to theta. Sorry. Okay, so for z, it was z was equal to r cosine theta. So its derivative with respect to r will be cosine theta. Yay! Da, 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 ba, bam. And the derivative with respect to cosine theta is minus r sine theta. So you just need to look at your derivative charts for the derivatives of sine and cosine to understand that the derivative of cosine theta is minus sine theta. And then here we're taking the derivative of y with respect to r, we get sine theta, and the derivative of y with respect to theta, we get r cosine theta. And then we have to take the determinant. The determinant, what you do is you multiply these two values here, going on this diagonal. So it's cosine theta times r cosine theta, which is r cosine theta squared. And you subtract the product of these two values on this diagonal here. So instead of minus, since we already have a negative, it'll be plus r sine theta squared. And we already know that cosine theta squared plus sine theta squared is equal to 1. So this equals r, right? Because you extracted the r out of this the summation. And then of course we take the absolute value of this, and since this is already positive, it's just going to be r. So now we can substitute r dr d theta for dx dy, right? So this is our scaling factor here. So we go ahead and make that substitution, and we still have to change the bounds of this integral. So for r, it's from 0 to infinity, so it's e raised to the minus r squared over 2. Remember, we're substituting r squared for z squared plus y squared, and then we get r dr d theta. And then for the d theta part, or for the theta part, it's going from 0 to 2 pi, because the theta ranges from 0 to 2 pi. We put our little friend 1 over 2 pi here, right? So now we're in pretty good shape. So let's go ahead and finish this up. Let's do a u substitution to simplify this integral again. So we'll let u equal, not well, me. Oh no, I'm sorry, not that kind of u. We'll let u equal r squared over 2, and then we take its derivative. So that's du equals, well, this is a very simple derivative, so it's 2r over 2, so the 2's cross out, right? And they get du equals r dr, which is awesome because we have an r dr here, so we can just easily substitute du for r dr. How beautiful, isn't it? So now we're left with this little sucker here. So we got e to the minus u du, and then we have the d theta. So let's go ahead and work this first integral out here. Well, its antiderivative, right, is minus e to the minus u from 0 to infinity. And then we still have, of course, 1 over 2 pi, the integral from 0 to 2 pi d theta, right? And this, so I just arranged it because e to the minus u is the same as 1 over e to the u. And you can, the reason I did this, you can see that in this part of the integral, we integrate this, we work with this part first here, right? And then we subtract we subtract again, setting u equal to 0. So in the first part, u is set to infinity. So this is going to be minus 1 over e to the u, where u is equal to infinity, minus 1 over e to the u, where u is set to 0. Well, as u approaches infinity, this approaches 0, so we don't have to worry about that because it gets really, really big. So it gets closer and closer to 0. U equals 0, e to the 0 is equal to 1, so we're going to have 1 there. So this is going to be 0 plus 1, right? Because again, we have a negative here, a negative, and a negative is a positive. Okay, so far so good, right? And then we have to deal with this d theta part here. Well, the antiderivative of d theta is just theta, right? Because theta, the derivative of theta is 1, and this is a 1 right here. So then we're going to have here, we're doing the same, right? We're going to do 2 pi minus 0, right? Because, again, this is just a theta here. So theta is going to equal 2 pi minus theta equals 0, so it equals 0. So we're left with 2 pi minus 0. Well, this gets pretty interesting here. So this is 2 pi minus 0 is 2 pi. 1 plus 0 is 1, so 2 pi times 1 is 2 pi. So we already have a 1 over 2 pi, and look at this. Yes, these cross out, and this ends up equal to 1. So we have just proven that this, indeed, this original function that we had here, where is it? This original function, I like that. That's pretty funny. Well, at least I think it's funny. This original function here is indeed a probability density function because it does integrate to 1. Okay, so look, this is I'm new to making these kind of videos with calculus. Last time I was in college and I had to take all the calculus courses in 1981 and 82. I think I finished my undergraduate college, many moons ago. So almost 40 years ago, right? So I had to, re-study calculus now again, a few years back, and I've been just having a blast with it. So I'm new to making videos with calculus, but there's nothing more fun than learning. And if you're going to be an expert in statistics, you better learn all this stuff. I mean, that's what I'm working on. But anyway, I hope you have a wonderful day, everybody. Bye, and I hope this helps.